Hi, in this mini lecture I will present with comparators. It is a family of devices which produce the result of comparison of two numbers, A and B. Let's call them A and B. And as humans, we can compare, yes, by looking at them, scanning the digits, and decide which one is greater, which one is lower. Perhaps they are the same. So let's put an example. If you've got two numbers without leading zeros, the shorter one will be lower. So the first is to, for humans, for people, is to scan the number of digits. The longer is greater. If they are the same, of the same length as in the digital systems, the compared numbers are always, or almost always, of the same length. You simply scan the digits, the corresponding digits, and compare the digits one after another, one by one. Okay, and people start rather doing this from the left-hand side, from the most significant bits, because if there is a difference in these bits, the remaining ones don't need to be compared at all, because yes, if 1 and 5 is are the most significant bits, and we see that B is greater than A, even if we don't look at the remaining bits. Okay. However, if you start doing the same in the other way, in other order, so start with this and go in this direction, it's quite odd approach for people, but it is common in the electronic devices. In this situation, you must compare and remember the comparison results to be considered for the next pair of digits, and so on. You must transform this information. You must have it in your mind when you do it. So, and you can change, or you change the result of the comparison many times until you reach the last digits. In this situation, is always the same decision, or always the same information is transferred, because always the corresponding digit of B is greater than A, but you can change. We like to have more interesting example. Let's have it this way, and let's do it this way. Okay, so here you've got A greater than B. Yes, A greater than B on this position. Go here. It is the same. A greater than B. What about this? That B you must change. B greater than A, because these are not important if there is a different situation in the higher bits. So higher bits decides, and you have changed, and you maintain with the same B equal greater than A in this way. Of course, if you've got the numbers which has the same higher bit, corresponding higher bit, and they differ a little bit later, let's say this, if you go in this way, the opposite way, you simply maintain equality until the first difference, and this difference decides, and you don't need to do it. Of course, in the electronic devices, in the digital systems, the numbers are scanned in this way or this way. All the digits are considered and are processed. Okay, so let's first focus on this situation, more familiar, and the humans are more familiar with. And let's switch to binary system. 1 0 1 1 0 1 1 0 1 0 1 1. Okay, let's go on. You do it iteratively. Okay, you must first compare. Let's start with this. You must compare the first digits. So you need to have such an element to compare two corresponding bits of the numbers AI, BI. Okay, AI, BI. So if you have AI, BI equal and the information from these bits are leading zeros, so they are equal on the left-hand side position. So the previous result is A equal to B, and the current bits are AI, BI are equal, 1, 1. You don't change this information, A equal to B. Okay? If the information is A equal to B and you've got 0, 0, the same situation. You don't change the information. But if the information was A equal to B, but you've got 0, 1, in this situation, A is lower than B, you change it. And the last situation is when you've got the opposite relation between the bits and A is greater than B. And this is maintained until the end of the comparison. This is the final result. How many cases do we have? 1, 2, 3, 4, 1 to 3 different cases of comparison, as you know, of course. So we must deliver the information using 2 bits, not a single, but 2 bits. Okay, let's call them P and Q, and let's derive the truth table for comparator. So P, let's call it I plus 1 because they come from the higher bit, Q plus 1, and the new, it is as was, as the current information, and the next information was is, and Pi is the output and Qi is the output to the neighboring right cell of the comparator. So we need a 1-bit comparator, but the one which can be connected to the other ones and combined to constitute to make n-bit comparator. In general, n-bit comparator, which is the following structure, which has the following structure. You've got the cells connected to each other in series, similar structure as in the case of other. The transmission of these signals are in the opposite direction, and this is the result. The result will be available on cell 0, comparing A0 with B0. And these are, let's say, A n minus 1, minus 2 and B n minus 2, and these bits are the most significant ones, A n minus 1, B n minus 1 for n-bit numbers. And encoding. We must encode 3 cases, A equal to B, A greater to B, and A lower to B, using the PQ, PI, QI in general signals. Let's assume that 0, 0 will be the signal of equality. 0 would be better than 1 on the left, because A is on the left is greater than B, let's say, and it is our choice as constructors. Okay, it is not a signal for the signal. Of course, is important for the user here, And we always can produce 3 different signals. Yes, if the user is interested in having 3 independent lines of A greater and equal A equal to B, A greater to B, and A lower to B, it is a kind of decoder. We can construct this decoder to have 3 lines instead of 2, but it is wiser to have it 2 because of the cost of the overall device. Greater equal lower, greater equal lower can be symbol of this cell. And the next step is to derive the truth table. I will do it partially only, okay? And to be completed at home, okay, by you. And what we have for this cell, we've got the previous information or result of comparison of the higher bits. We've got also the values of the current bits. And we must produce the proper information to the lower, to the right-hand side neighboring cell. So we can start with all zeros and we finish with all ones. As usual, all the cases can be stated here and we put here because we've got only 4 variables, but we could construct, we will construct the comparators of any number of bits. 0, 1, 0, 0, 0. Half of the table will be present here. And the remaining part, the remaining half, you please are supposed to fill in. Okay, so the information is that the numbers were equal on the higher bits and the current bits are 0, 0, so the same information. They are the same, including the current bits, still the same. In the second row, the information is they were the same, they were equal, but currently B is greater. The current bit of B is 1 and the current bit of A is 0, so B is greater than A, B is greater than A is 0, 1. Information is here in this table. So 0, 1 is the second row output, and for the third row, the opposite, 1, 0, and 0, 0, okay? The information states that the numbers were the same and currently are also the same, so you don't change this equality information. In the case of 0, 1 on PQ, 0, 1 means this, and because you traverse from left to right on the higher position, so higher positions decided already, yes? On the higher positions was this. So the lower positions, the current are lower with respect to this result, don't have any influence on the results. So you simply copy the result. 0, 1, 0, 0 gives you 0, 1. The same information without any change should be copied on the output until the end of the chain of the comparator cells. And please do the same, paying attention of the state of the values of PQ which are not stated here in this table. 1, 1 is not used. Yes, 1, 1. What about 1, 1? 1, 1. 1, 1 is not used and can be then used for minimization purposes. So if you go lower to the bottom of this table, when you have 1, 1 in 4 rows, you would have 1, 1 on P and Q. You simply put don't cross states for these to have it minimized in a more compact way, the cheapest solution. Okay. Oh, what's very important is to put the equality here. Equality. If you start doing this, you don't assume they are different. Okay, the first bits are here, so you deliver the proper information for this first cell, because there are no more bits, you must deliver equality on these bits. Thank you.